Back to another video, guys. I picked up a very interesting problem dedicated to circles which share a common point. Okay, it's mostly connected with circle theorems, but the main trick is in a bit different things. Okay, let's have a look there. Here's the problem. Try to pause the video, try to do by your own, and let's get started. So we have two circles with centers, let's say O1 and O2. Okay, let's say this is O1, this is another center, let it be O2. Okay, and we are given that GF is the tangent, so that means it's tangent to both circles, and we're also given the length GF, that is 10 centimeters. Okay, we fix that, and right now we're gonna go back to the areas. So areas of the circles are in the ratio 4:9. You need to find the area and the circumference of the large circle. So what I'm gonna do first, I just want to put two radius, so here and here. And we know that by circle theorems, we know that the radius is perpendicular to the tangent. So if I say that this is the big radius and this is the small one, we know that two segments R, big R, and small r, they are parallel, okay, to each other, and they also range 90 degrees angle. So that's the first notice. And also, because A is the common point of two circles which are actually shares this point between each other, so we can say that if we put, let's say, that blue line connecting the centers, the segment O2, O1 should go through the common point A. Why? Because if you have a look here, you understand that if you put the tangent line that goes through the point A, which is a common one, both radius, the big one, which is R, and the small one, which is R small, are going to be perpendicular to this common line. So that's why they will arrange two angles which are each one 90 degrees. And that's why in total we have a straight line segment. So that's why we prove that O1, O2 segment is a straight line segment. So this is very necessary. Straight line segment. Okay. So we prove that because in total we'll have 90 degrees over open angle. Okay, we prove that. And now how to figure out first the area and circumference of the large circle. Okay, I draw just by definition, let it be the area of the biggest circle of the largest one, so that's pi r squared, and circumference, which is basically the length of the boundary along the circle, is going to be 2 pi capital R. The main purpose is to find R. So we set up the goal to find big radius, or the radius of the largest circle. But how? There is nothing, okay, except for we are given the areas of circles are in the ratio. Okay, so let's use this fact. Because the ratio is 4:9, obviously this is the area of the small circle to the area of the big one, which is actually, if you rewrite through the formula, it's going to be pi r squared over pi r capital R squared, which is going to be simply r squared over r squared, our big R squared. That's going to be 4/9. Or in other words, you can say that if you take the square root of both parts, you'll get small to the big one is going to be 2/3. Okay. From there, you can express, let's say, small radius through the big one. Okay, that's the first step. However, we need to have another equation which connects the small radius and the big radius. And what I can do, because those actually pre-built that we made, it's not for sake, so we are going to use right now in a moment. And we just want to connect with a parallel line center O1 with another point. Let's say maybe better to use, okay, Let's connect more proper way, in more proper way. Okay, this one. And let's set up the point here. That's going to be, let's say, point K. But I'm not going to draw, I'm not going to put that as a label. So I just shade the triangle that we're interested in. So from the shaded triangle, we can say that this angle is 90 degrees angle, definitely. Why? Because the segment, this segment is simply FG that I lift up a little bit, okay? And I lift exactly by the distance small r. I just lift it up, okay? And I put the parallel line that is equal to FG. So that's why we can state that the segment is going to be 10 centimeters. So we have, in other words, we have a triangle with 10 centimeters here at the bottom part, some, let's say, lateral side, another leg, and hypotenuse. So obviously hypotenuse is this blue one, it's represented by the sum of radius. So it's going to be big radius plus the small radius. And this small part, which is right there, okay, which is simply right there, just I mark here, okay. So this small segment is simply the difference, because the whole length, this is the radius, right? The whole length is just the radius. This is the radius, big radius. And the small one, we can find the small segment, we can find by subtracting the small radius r, which is right there. Okay, so that's why, indeed, this is the difference between big radius and the small one. And we'll have a right angle triangle. Okay, so the bottom part is 10, because we'll simply lift up FG parallel way, because two radius, so the big one and small one, they are parallel segments. So that's why we keep the length FG the same. Okay, so we have right angle triangle. Why not to use Pythagoras? Okay, Pythagoras for this triangle. It simply works as the difference squared plus 10 squared, which is 100. Okay, I put 10 squared for a while. And here is going to be the sum of sides. That's what we have right now. I squeeze a little bit. I just lift it up. Okay. And what I'm going to do, I'm just going to simplify that. If I square it up, I will use the formula a plus minus b squared, which is a squared plus minus 2ab and plus b squared. And now I just apply it to the radius, what I have here. So this will give me r squared minus 2r big R plus r squared plus 100. And on the right side, I will apply the same formula here. And I'll get the big R squared plus double product and plus small r squared. And now I see definitely that I can cancel those similar terms because they are on both sides equal. And finally, what I've got that 100 will be equal to 4 small r and big R, because that what I have, I just transfer there and I add them up. Okay, so that's why the small radius by the big radius is going to be 25. Okay, now what I'm going to do, I have the second equation finally. So this is the first equation, and this is the second one. So I just combine them, and from there, from 1, I just simply express, let me express the small r, because our final goal is to find the area and circumference of the largest circle. So that's why what we're going to do, we can, from 1, we can express small radius is 2 over 3 of the big one. And if we plug that here and 2, we'll get the result. Okay, we'll get the result 2 over 3 r squared will be equal to 25. So that's why From there, r is gonna be taking the square root, 5, and square root of 2 over 3. Square root of 2 over square root of, sorry, the way back, because I multiply by 3 both parts, so I multiply by 3 over 2 actually both parts, and taking the square root, I will get square root of 3 out of square root of 2. Okay, that's the final expression for the radius, that what I'm going to have. Okay, so this is the final expression for the radius. And right now, if you want, you can calculate, but I leave insert form. And now we just can go back to a area and the radius. Just plug in. So area is going to be pi times r squared, which is actually 25 times 3 and over 2. So times 3 is going to be 75 over 2 pi. 75 pi over 2. If you like, you can calculate, but you got the logic. And circumference is simply 2 pi times the radius, which is simply 5 square root of 3 over square root of 2. So that's the final formula that I have for the area and for the circumference. That's definitely challenging math, so I may say that. But make sure you understand that and you can work out using circle theorems. If you like that, please like this video and subscribe if you're new here. And don't forget to check A-level Zillions classes for more A-level stuff. And also you can visit my A-level program if you're just A-level student and refresh something from GCSE. See you next time.